Hello everyone. Welcome back to another fascinating journey through geometry. Let me ask you something. Have you ever watched a car tire touch the road? It rolls smoothly, but at any instant, it touches the ground at only one point. That single contact point is what we call a tangent in geometry. Now, mathematically speaking, a tangent to a circle is a straight line that touches the circle at exactly one point. We call that single point the point of contact. If you try to move the line slightly inward, it cuts the circle, becoming a secant. And if you move it outward, it no longer touches the circle at all. So a tangent is that perfect in-between line, just touching, never crossing. At any given point on the circle, there can be only one tangent, but a circle itself can have infinitely many tangents all around its boundary. Pause. Isn't it amazing how such a simple concept defines the rolling motion of wheels, coins, and even planets in orbit? Now here comes one of the most elegant results in geometry. When you draw a tangent to a circle at any point, and you also draw the radius to that same point, what happens? They meet at a right angle. Yes, the tangent is perpendicular to the radius at the point of contact. So if you name the center as O, the point of contact as T, and draw the tangent as PT, then angle OTP equals 90 degrees. This means the line joining the center and the point of contact acts as a normal line, or in simpler words, a line that's at right angles to the tangent. Conversely, if you already have a line that's perpendicular to the radius at the end of the circle, that line will always be a tangent. This perpendicular property is the foundation of all tangent theorems you'll learn ahead. And it's what engineers use to ensure circular objects roll perfectly without slipping. Let's move ahead. Suppose there's a point P lying outside the circle. Can you draw tangents from that point to the circle? Of course, you can draw two tangents, touching the circle at points T1 and T2. Here's something interesting. Both these tangents are equal in length. Yes, from the same external point, the lengths of both tangents are identical. Mathematically, we write this as PT1 equals PT2. And this happens because the two triangles OPT1 and OPT2 are congruent. That means they have equal sides and angles. So, whether it's a car moving around a curve or a light beam reflecting off a circular mirror, this property ensures perfect balance and symmetry. Now let's prove that the tangents drawn from an external point to a circle are equal. Given a circle with center O, an external point P, and two tangents PT1 and PT2 touching the circle at T1 and T2. To prove PT1 equals PT2, construction, join OT1, OT2, and OP. Since the tangent is perpendicular to the radius at the point of contact, angle OT1P equals 90 degrees, and angle OT2P equals 90 degrees. Now look at the triangles OPT1 and OPT2. In both triangles, OT1 equals OT2, radii of the same circle, OP equals OP, common side, and both have a right angle. Hence, by the RHS congruence rule, the two triangles are congruent. Therefore, PT1 equals PT2. This simple yet powerful result appears in many geometry proofs, so keep it handy. Now let's take it one step further with a very useful theorem, the tangent secant theorem. Imagine you have a circle and an external point P. From P, you draw one tangent PT and one secant that cuts the circle at points A and B. The theorem says, the square of the tangent's length equals the product of the secant's external part and its total length. That is, PT squared equals PA multiplied by PB. This relation connects tangents and secants beautifully. One outside, one cutting through, both linked by pure geometry. Example, if PA equals 6 and PB equals 10, then PT equals square root of 6 multiplied by 10, which equals square root of 60, or approximately 7.75 units. This theorem forms the backbone of several board exam problems and real-world applications, from designing circular arches to optical lenses. Now let's derive an important formula, the length of a tangent drawn from an external point. Given circle with center O, radius R, and an external point P. A tangent PT touches the circle at T. We need to prove that PT equals square root of OP squared minus R squared. Let's see how. In right triangle OPT, we know that OT is perpendicular to PT. So by the Pythagoras theorem, OP squared equals OT squared plus PT squared. Now, replacing OT by radius R, we get PT squared equals OP squared minus R squared. Taking the square root on both sides, PT equals square root of OP squared minus R squared. And that's the formula. This means if you know how far the external point is from the center and the circle's radius, you can calculate the tangent length instantly. Example, if OP equals 13 and R equals 5, then PT equals square root of 13 squared minus 5 squared. That is square root of 169 minus 25, which equals square root of 144, or simply 12 units. Neat, right? Now let's connect this to the real world. Tangents are everywhere, from wheels and gears to curved roads and racetracks. Engineers use tangent principles to design smooth turns on highways, ensuring vehicles transition safely from straight paths to curves. In mechanical engineering, tangents help in gear tooth design, so gears mesh perfectly without slipping. Even in satellite communication, tangent lines define the edge of signal coverage, where the antenna just touches the Earth's horizon. And in physics, tangents play a key role in circular motion, because the direction of instantaneous velocity is always tangential to the circular path. So you see, what started as a simple line touching a circle once turns out to be a principle shaping technology, design, and science all around us. Let's wrap up everything we learned today. A tangent is a line that touches a circle at exactly one point. It is perpendicular to the radius at the point of contact. From an external point, two tangents can be drawn, and both are equal in length. We also explored the tangent secant theorem, where PT squared equals PA multiplied by PB. Finally, we derived the formula PT equals square root of OP squared minus R squared for finding tangent length. Tangents may look simple, but they're one of the most elegant connectors between algebra, geometry, and the real world. And that's how we understand tangents to a circle, from their definition to their amazing real-world applications. In the next video, we'll explore circle theorems and their proofs. So stay tuned and keep exploring the beauty of geometry. Finally, we proved that the length of a tangent from an external point P is given by PT squared equals OP squared minus R squared. Understanding these fundamental circle properties lays the groundwork for the upcoming theorems, like the tangent secant theorem and properties of cyclic quadrilaterals. And that's the complete introduction to circles. In the next video, we'll dive deeper into tangents to a circle and uncover some fascinating geometric truths. Thank you for listening. See you in the next concept.